Welcome to where time falls quiet.
Forbidden Relic, the Sumerian tablet that rewrites history. Take a moment to subscribe, so this place of calm is always here for you. What if the first mathematicians weren't Greek philosophers debating in marble courtyards, but scribes working in the shadow of ziggurats, pressing calculations into wet clay under a Mesopotamian sun that burned 5,000 years ago? What if the foundations of mathematics, the language we use to describe reality itself, didn't begin with Pythagoras or Euclid, but with hands we've forgotten, speaking a truth we've only just started to hear again? In 1922, a team of archaeologists working in the ruins of ancient Nippur, in what is now southern Iraq, unearthed a fragment of the past that refused to fit the narrative we'd constructed about human progress. It was small, unremarkable in appearance. A clay tablet no larger than a smartphone, its surface covered in the wedge-shaped impressions of cuneiform script. The clay was the color of dried blood, baked hard by millennia of heat and pressure beneath layers of sediment. The excavators catalogued it with clinical precision, assigning it the designation CBS 10673, and shipped it to the University of Pennsylvania Museum, where it would sit, largely ignored, for decades. The tablet was filed among thousands of others: administrative records, grain inventories, temple accounts. The detritus of bureaucracy from a civilization that had mastered the art of record-keeping before most of humanity had learned to write at all. No one understood what they were looking at. The cuneiform was clear enough, the sexagesimal notation familiar to scholars of ancient Mesopotamia. But the content, the actual mathematical operations pressed into that clay, remained opaque. It would take another generation before anyone truly read what the Sumerians had written. And when they did, the implications were immediately, profoundly unsettling. Imagine holding that tablet in your hands. Feel the weight of it, deceptively heavy for its size. The surface isn't smooth. Your fingers trace the wedge marks, each one pressed deliberately into wet clay by a reed stylus held by someone who knew exactly what they were doing. The clay remembers the pressure of those fingers, the angle of the stylus, the intention behind each mark. It remembers in a way that paper never could, in a way that even stone struggles to match. Clay is patient. Clay waits. And when we finally learned to listen, the clay spoke. The tablet contains 15 rows of numbers, arranged in 4 columns. At first glance, it appears to be a simple mathematical table, the kind of thing a student might create as an exercise, working through basic calculations to demonstrate competence. This is what scholars assumed for years. A pedagogical tool, nothing more. But in 1945, a mathematician named Otto Neugebauer examined the tablet with fresh eyes, and the breath left the room. The numbers weren't random exercises, they were Pythagorean triples. Sets of 3 integers that satisfy the equation we now write as a squared plus b squared equals c squared. The relationship that defines right triangles, that underpins trigonometry, that forms the foundation of geometry itself. The Sumerians who created this tablet had calculated 15 different Pythagorean triples, arranged them systematically, and recorded them with perfect accuracy. The precision is extraordinary. The largest triple on the tablet, 12,709, 13,500, and 18,541, demonstrates a computational sophistication that wouldn't be matched in the ancient world for over a millennium. These aren't approximations or lucky guesses. They're exact solutions, derived through a systematic method that shows complete mastery of abstract mathematical principles. But here's where the silence begins to hum with implications. Pythagoras, the Greek mathematician traditionally credited with discovering this relationship, lived around 570 BCE. The tablet from Nippur dates to approximately 1800 BCE. That's a gap of 13 centuries. 1,300 years before Pythagoras was born, Sumerian scribes were calculating Pythagorean triples with algorithmic precision. The mathematical relationship we name after a Greek philosopher was already ancient knowledge when Greek civilization was still struggling to emerge. The conventional explanation crumbles under even gentle scrutiny. Perhaps the Sumerians discovered this relationship independently, through trial and error, through the gradual accumulation of practical knowledge about construction and land surveying. But the tablet shows no signs of such evolution. There are no mistakes, no corrections, no progressive refinement. The mathematics appears fully formed, presented with the confidence of established curriculum. The scribes weren't discovering these relationships. They were recording them, preserving knowledge that already existed in complete form. Consider what this means. Mathematical understanding of this sophistication doesn't spontaneously generate. It requires infrastructure, a tradition of scholarship, institutions dedicated to learning, generations of teachers and students refining techniques and building on previous work. It requires, fundamentally, time, deep time. Time to develop the conceptual framework, time to create the notation system, time to train the minds capable of thinking in pure abstraction. The Sumerian civilization, as we understand it, emerged seemingly overnight around 3200 BCE, already possessing writing, mathematics, astronomy, architecture, and law. There was no apprenticeship period, no fumbling toward literacy. They arrived on the stage of history fully dressed. The clay tablet CBS 10673 isn't just a mathematical document. It's a challenge to the entire narrative of human progress that we've constructed. The narrative that says, civilization is a ladder we climb, rung by rung, from primitive to sophisticated, from simple to complex. The tablet suggests something else, something that makes the hair stand up on the back of your neck when you truly consider it. It suggests that the Sumerians weren't inventing mathematics. They were remembering it, copying it, preserving fragments of understanding that came from somewhere or somewhen else. In the museum archive, the tablet rests in its climate-controlled case, protected from the very air that would slowly return it to dust. The cuneiform marks are still sharp, still clear, still speaking across 40 centuries with perfect clarity. The clay remembers what we forgot. It remembers a sophistication that shouldn't exist, calculations that weren't supposed to be possible, knowledge that has no clear source. And if you press your palm against the glass, if you imagine the warmth of that clay when it was still soft, still receiving the impressions of the stylus, you might feel it too. The weight of inheritance, the burdens of proof. The uncomfortable truth that everything we think we know about the dawn of civilization might be built on the ruins of something we've chosen not to see. There's a particular kind of silence that exists in museum archives. Not the silence of emptiness, but the silence of accumulated time, of objects waiting to be understood, of stories pressed into clay and stone and papyrus that no one has yet learned to hear. The University of Pennsylvania Museum possessed one of the world's finest collections of cuneiform tablets, tens of thousands of fragments excavated from the cities of ancient Mesopotamia. Most had been catalogued with meticulous care, photographed, translated, filed away in drawers that lined corridors where scholars walked with hushed steps. Among these thousands of voices from the past, tablet CBS 10673 waited in its drawer, speaking a language that no one was yet equipped to understand. The initial assessment was dismissive, almost casual. A student exercise, the cataloguers decided. The tablet's contents appeared to be mathematical tables, the kind of repetitive drills that scribal schools use to train young minds in the fundamentals of calculation. Ancient Mesopotamian education was rigorous, demanding. Students copied legal documents, practiced writing administrative records, and worked through mathematical problems until their hands ached and the cuneiform script became as natural as breathing. This tablet, with its neat rows of numbers and systematic organization, seemed to fit perfectly into that pedagogical tradition. It was filed accordingly, assigned a catalogue number, and forgotten. Just another training exercise from a civilization that had excelled at bureaucratic precision. For decades, the tablet remained in its drawer, untouched except for the occasional graduate student seeking primary sources for research papers on Mesopotamian education or number systems. The scholars who glanced at it saw what they expected to see. Evidence of mathematical instruction, proof that the Sumerians had developed systematic methods for teaching arithmetic. No one questioned the assumption. No one looked deeper. The tablet was performing exactly the function the archive demanded of it, serving as a data point in a larger narrative about ancient pedagogy. The truth it contained remained locked behind familiarity, hidden by the very expertise that should have revealed it. Then, in 1945, everything changed. Otto Neugebauer, a mathematician and historian of ancient Theisch, requested access to the museum's Mesopotamian mathematical texts. Neugebauer possessed a rare combination of skills, deep expertise in both ancient languages and modern mathematics. He could read cuneiform as fluently as he could work through complex algebraic equations. More importantly, he approached ancient texts not as historical curiosities but as active mathematical documents, written by minds as sharp and sophisticated as any modern mathematician. When he examined CBS 10673, he didn't see a student exercise. He saw something that shouldn't exist. The recognition wasn't immediate. Neugebauer worked through the tablet systematically, translating each column, checking the calculations against known Mesopotamian mathematical practices. The first column contained a sequence of numbers that seemed random at first glance. The second column held larger numbers, also apparently arbitrary. But as he worked through the third and fourth columns, a pattern emerged. These weren't random numbers. They were related. Specifically, they were integer solutions to the equation that defines right triangles. Each row represented a Pythagorean triple, 3 whole numbers where the sum of the squares of the first two equals the square of the third. The tablet contained 15 such triples, calculated with perfect precision. The implications hit him with physical force. Neugebauer understood immediately what he was looking at. This wasn't a student exercise. This was advanced mathematics, presented in a form that suggested systematic generation through algorithmic methods. The Sumerians hadn't stumbled upon these numbers through trial and error. They had calculated them using a consistent technique that could generate an infinite series of such triples. The mathematics displayed on the tablet was sophisticated enough to be published in a modern mathematical journal. And it predated Pythagoras, the man whose name is attached to this fundamental relationship, by over a millennium. Neugebauer's published analysis sent ripples through the academic community. Not earthquakes, not revolutionary upheaval, but ripples. uncomfortable ripples that scholars tried to smooth away with explanations that preserved the comfortable narrative. Perhaps the dating was wrong. Perhaps the tablet was from a later period, misfiled or misidentified during the chaotic excavations of the early 20th century. But the stratigraphy was clear. The tablets came from layers dated conclusively to the Old Babylonian period, roughly 1800 BCE. The dating wasn't approximate or disputed. It was definitive, confirmed by surrounding artifacts and the archaeological context of the excavation. Others suggested that the Sumerians must have developed this mathematics independently, through purely practical means. Building construction, land surveying, the division of agricultural plots all required some understanding of right angles and proportional relationships. Perhaps over centuries of practical application, Mesopotamian builders and surveyors had gradually accumulated enough empirical knowledge to recognize these numerical patterns. But this explanation dissolved when confronted with the systematic of the tablet. These weren't practical measurements. They were pure mathematics, abstract relationships between numbers with no obvious connection to physical construction. The triple 12,709, 13,500, 18,541 isn't something you discover while building a temple or surveying a field. It's something you calculate using sophisticated mathematical techniques. The most troubling aspect wasn't just the mathematics itself, but the complete absence of development. When we study the history of mathematics in other cultures, we see evolution. We see mistakes, corrections, refinements. We see simpler techniques gradually giving way to more sophisticated ones. Egyptian mathematics, Greek mathematics, Chinese mathematics all show clear developmental arcs, with each generation building incrementally on the work of the previous one. But Sumerian mathematics appears already mature, already sophisticated, as if it emerged fully formed from some unseen source. There are no primitive earlier versions, no fumbling attempts, no gradual progress from simple to complex. The tablets we possess from the earliest periods of Sumerian literacy already demonstrate mathematical sophistication that wouldn't be matched in the Western world for thousands of years. In the archive, scholars debated, papers were written, conferences were held, explanations were proposed and defended, and sometimes abandoned. The tablet remained in its drawer, now recognized as significant, now studied and photographed and analyzed with tools its creator could never have imagined. But recognition didn't bring understanding. If anything, the more closely scholars examined CBS 10673, the more inexplicable it became. Each new analysis revealed additional layers of sophistication. The arrangement of the triples wasn't random. They were organized according to a principle that suggested the scribe understood not just how to calculate these numbers, but why they worked. What mathematical relationships governed their behavior. The comfortable assumption that the Sumerians were simply clever, that they had discovered these mathematical relationships through their own ingenuity, began to crack. Because cleverness, no matter how profound, requires time to develop. It requires a learning curve, a progression from ignorance to understanding. And that progression was absent. The mathematics on the tablet appeared with no antecedents, no simpler versions from earlier periods, no evidence of the experimental phase that must precede any genuine breakthrough. It was as if someone had handed the Sumerians a completed mathematics curriculum and told them to copy it, preserve it, transmit it to future generations without necessarily understanding where it came from or how it was originally derived. Stand in that archive now, in the silence that hums with accumulated knowledge. The tablet rests behind glass, its surface still bearing the marks of fingers, that pressed those calculations into wet clay 40 centuries ago. The numbers are still clear, still correct, still challenging every assumption about the linear progress of human understanding. And in that silence, if you listen carefully, you can hear the question the tablet poses. Not who created this mathematics, but who gave it to them? Who taught the teachers? Where is the source? Numbers are never just numbers. They are choices, decisions embedded in notation systems that reveal how a culture thinks about quantity, about relationship, about the structure of reality itself. When we write the number 60, we use two symbols from a decimal system inherited from fingers and toes, the most primitive counting tools humanity possessed. But when a Sumerian scribe wrote 60, they used a single symbol, because 60 wasn't just another number in their system. It was the foundation, the base, the architectural principle upon which all other numbers were built. We call this system sexagesimal, base 60, and it survives today in fragments we barely notice. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. Fossils of Sumerian thought embedded in the measurements we use without thinking. The tablet CBS 10673 uses this sexagesimal notation with effortless fluidity. Each number is constructed from combinations of symbols representing ones and tens, building up to 60 before the pattern repeats in a higher order of magnitude. To modernize, it seems cumbersome, unnecessarily complex. Why base 60 when base 10 is so much simpler, so much more aligned with human physiology? But this question reveals our own limitation. We assume simpler is better, that efficiency drives innovation. The Sumerians chose base 60 for reasons that had nothing to do with counting on fingers. They chose it because 60 is mathematically elegant in ways that 10 could never be. 60 is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60 itself. It allows for fractional calculations of extraordinary precision without requiring decimal notation. It is fundamentally a more sophisticated choice than the system we use today. But the true revelation hidden in the tablet's notation isn't mathematical elegance. It's astronomical precision. When scholars finally understood what they were looking at, when they moved beyond the Pythagorean triples to examine the relationships between the numbers themselves, a pattern emerged that shouldn't exist. The ratios embedded in the tablet's calculations correspond to celestial mechanics. Specifically, they track the synodic periods of planetary motion, the complex dance of celestial bodies, as observed from Earth. The numbers encode relationships between Venus and Earth, between Mars and Jupiter, cycles that require sustained, precise observation over decades or even centuries to calculate accurately. Imagine standing in ancient Sumer, your eyes turned to the night sky. The stars move in patterns so regular they seem eternal, wheeling overhead in the same configurations your ancestors saw. But there are wanderers among them, bright points of light that refuse to follow the fixed paths of the stellar background. The Greeks would call them planets, wanderers, and spend centuries trying to explain their seemingly erratic movements. To track a planet's synodic period, you must observe it night after night, year after year, noting when it rises in the same position relative to the stars, when it appears to move backward against the stellar background, when it vanishes in the glare of the sun only to reappear weeks later. This requires not just observation, but systematic record-keeping, mathematical modeling, and conceptual frameworks sophisticated enough to distinguish apparent motion from actual motion. The Sumerians possessed all of this. Their astronomical texts track Venus with precision, that wouldn't be matched until the invention of the telescope. They calculated the synodic period of Venus as 584 days, accurate to within a fraction of a percentage point. They knew that 8 Earth years equal 13 Venus years, a relationship so precise it allows for eclipse prediction and planetary conjunction forecasting. But here's the unsettling part. There are no records of the observation process. No training manuals explaining how to track planetary motion. No progressive refinement of astronomical models. The knowledge appears complete, presented in texts like CBS 10673 with the confidence of established fact rather than recent discovery. The conventional explanation invokes patience and dedication. The Sumerians must have spent generations observing the sky, we're told. Priests stationed on ziggurats watching the heavens night after night, slowly accumulating the data necessary to recognize these patterns. But this explanation fractures when confronted with the precision involved. To calculate synodic periods with the accuracy demonstrated in Sumerian texts requires not just observation, but correction for atmospheric refraction, adjustment for the observer's latitude, compensation for the Earth's axial tilt. These are not intuitive corrections. They require understanding that the Earth itself is moving, that our position is not fixed, that what we see is not precisely where celestial objects actually are. The Sumerians demonstrated this understanding in their calculations, yet their cosmology, as recorded in their myths, describes a flat Earth beneath a solid sky dome. The mathematics contradicts the mythology. Consider what this means. Either Sumerian astronomers possessed observational and computational tools far more sophisticated than anything they left physical evidence for, or they were working from templates, from inherited knowledge that they copied and preserved without fully understanding its theoretical foundations. The tablet suggests the latter. The calculations are too precise, too complete, too free from the errors that would inevitably accumulate during the learning process. They read like answers copied from a textbook, not discoveries painstakingly derived through original research. And if they are copies, where is the original? Where is the source text from which these astronomical calculations were transcribed? The sexagesimal system itself hints at the answer. Base 60 isn't a natural choice for a culture developing mathematics from scratch. It's too complex, too sophisticated for early-stage calculation. But it's perfect for astronomy, for dividing circles, for tracking celestial cycles that subdivide naturally into factors of 60. The choice of base 60 suggests that Sumerian mathematics was designed for astronomical calculation from its inception, that the number system wasn't adapted to astronomy, but astronomy demanded the number system. This is backwards from how we understand mathematical development. Tools should evolve to meet needs, not spring into existence perfectly suited to complex applications. Unless, of course, the tools weren't evolved but inherited, passed down from a source that had already optimized them for precisely these purposes. The tablet speaks in the language of the cosmos, recording relationships between celestial bodies with a precision that requires either telescopic observation or access to calculations performed by those who possessed such tools. Neither possibility fits comfortably within the accepted narrative of human civilization's development. Telescopes didn't exist in 1800 BCE. No physical evidence suggests anything remotely comparable to optical magnification technology in ancient Mesopotamia. And yet, the calculations encoded in base 60 notation on clay tablets scattered across museums worldwide demonstrate knowledge that shouldn't be accessible to naked-eye observers, no matter how patient or dedicated. There's a weight to this realization that settles in the chest like stone. We want history to be progressive, linear, building from simple to complex through accumulation and innovation. We want the Sumerians to be impressive but comprehensible, clever but not impossibly sophisticated. The tablet refuses this comfort. It insists that the mathematics, the astronomy, the notation system itself represent not innovation but inheritance. That somewhere in the unrecorded past, before the first cuneiform was pressed into clay, someone was watching the stars with instruments and understanding we've only recently recovered. And that knowledge, filtered through catastrophe and cultural collapse, survived in fragments, copied by scribes who preserved what they could no longer fully comprehend. The clay tablet rests in its archive, its sexagesimal calculations still speaking across 40 centuries. The numbers track planets with precision, encode astronomical relationships with accuracy, demonstrate mathematical sophistication that challenges every assumption about ancient capability. And in the silence between the symbols, in the gaps where explanation should exist, the tablet poses its quiet, insistent question. How did they know? Not what did they know, but how? Where are the observations, the instruments, the developmental stages that must precede such knowledge? Where is the learning curve? Where, ultimately, is the source from which this river of wisdom flows? In the mythology of ancient Sumer, there exists a concept so fundamental to their understanding of civilization that it appears in nearly every major text: the me. The word defies simple translation, carrying connotations that blend divine decree, cultural practice, cosmic law, and practical knowledge into a single, untranslatable whole. The me encompassed everything from kingship and priesthood to music and mathematics, from the art of metalworking to the principles of justice. These weren't human inventions according to Sumerian belief. They were gifts, handed down from the gods who dwelt in the Abzu, the primordial waters beneath the world, the deep from which all wisdom emerged. We dismiss this as mythology, as primitive attempts to explain cultural development through supernatural narrative. But what if we're reading the texts backwards? What if the mythology isn't explaining the origin of knowledge, but preserving the memory of its transmission? The Sumerian creation myths describe the god Enki, lord of wisdom, dwelling in the Abzu and possessing all the me. He guards them, distributes them to worthy recipients, occasionally loses them to clever goddesses who steal them for humanity's benefit. These stories are colourful, dramatic, full of trickery and divine politics. But beneath the mythological narrative runs a consistent thread. Civilization didn't emerge organically from human effort. It was transferred, complete and functional, from a source that predated human society. The me weren't discovered through trial and error. They were received, learned, copied, preserved. The Sumerians saw themselves not as innovators but as inheritors, custodians of knowledge that came from before, from elsewhere, from the deep. Now consider tablet CBS 10673 through this lens. The mathematical sophistication it displays isn't framed as a Sumerian achievement. There are no colophons boasting of the scribe's brilliance, no attributions to a particular mathematical genius who revolutionized calculation. The tablet presents its contents with bureaucratic plainness, as if these calculations were as ordinary as grain receipts or temple inventories. This is the tone of copying, not discovery. The scribe who pressed these numbers into clay was preserving knowledge, transmitting it, ensuring its survival through the technology of writing that had only recently become available. The mathematics existed before the tablet. The tablet merely captured it, fixed it in physical form so it wouldn't be lost when the memories faded. This interpretation explains what conventional narratives cannot: the absence of mathematical evolution in Sumerian texts. When we examine mathematical documents from other ancient cultures, we see progression. Egyptian mathematics develops from simple addition and subtraction to more complex operations over centuries. Greek mathematics builds systematically from basic geometry to sophisticated theoretical frameworks. Chinese mathematics shows clear stages of advancement, with each generation refining and expanding the work of predecessors. But Sumerian mathematics appears already complete. The earliest mathematical texts we possess demonstrate competence in algebra, geometry, and numerical analysis that wouldn't be surpassed for millennia. There are no primitive versions, no learning stages, no gradual accumulation of technique. The knowledge is simply there, present from the moment writing allows us to see it. The same pattern appears across every domain of Sumerian culture. Their legal codes, like the Code of Ur-Nammu, dating to approximately 2100 BCE, display sophistication in jurisprudence that suggests centuries of refinement. Yet, it's one of the first legal codes we possess, appearing with no obvious antecedents. Their astronomical texts track celestial phenomena with precision that requires long-term observation and mathematical modeling. Yet these texts emerge already sophisticated, with no records of the observational process that must have preceded such knowledge. Their architectural techniques, their irrigation systems, their administrative bureaucracies all display the same troubling pattern. They appear fully developed, as if civilization didn't gradually build toward complexity, but inherited it from a source that remains frustratingly invisible in the archaeological record. The me in this light aren't mythology, they're memory. They're the Sumerian attempt to preserve the truth that their civilization was built on foundations they didn't lay, using knowledge they didn't originate. The mythological framework, the gods and the Abzu and the divine transmission of wisdom, might be the only language available to describe a reality that the Sumerians themselves didn't fully understand. How do you explain that your mathematics, your astronomy, your architecture all came from before, when you have no clear record of that before? You say the gods taught you. You say the knowledge came from the deep. You preserve what you can and transmit it faithfully, even if the origin story has become confused in the transmission. This interpretation faces immediate resistance from conventional archaeology and history. Where is the physical evidence of this prior civilization? If the Sumerians inherited their knowledge, where are the ruins of the culture that taught them? Where are the artifacts, the texts, the traces that must exist if a sophisticated civilization predated Sumer? These are fair questions, and they deserve consideration. But absence of evidence isn't evidence of absence, particularly when we're discussing events that occurred before written records, before systematic archaeology, in a region that has been continuously inhabited and rebuilt for 5,000 years. The Tigris and Euphrates valleys have been farmed, flooded, conquered, and reconstructed countless times. Archaeological contexts have been destroyed by millennia of human activity. If an earlier civilization existed and ended catastrophically, its physical traces might be minimal, buried beneath meters of sediment, eroded by water, or simply built over by successive cultures. Moreover, we do have traces. They're just not the kind of evidence that fits comfortable narratives. We have mathematical tablets that shouldn't exist. We have astronomical knowledge that requires observational capabilities beyond what the technology of the time should allow. We have architectural precision that challenges our understanding of ancient engineering. We have myths that consistently describe civilization as received rather than invented. Each piece of evidence taken alone can be explained away, but taken together they form a pattern that grows increasingly difficult to dismiss. The pattern suggests that the Sumerians were telling the truth in the only language available to them when they said their civilization came from before, from the deep, from the gods who guarded knowledge in the Abzu. The tablet CBS 10673 sits at the heart of this pattern. Its Pythagorean triples, calculated with algorithmic precision 13 centuries before Pythagoras, represent knowledge that has no clear developmental arc. The mathematics appears complete, functional, ready for use. It reads like curriculum, like teaching material designed to transmit understanding from one generation to the next. But if it's curriculum, who designed the course? If it's teaching material, who were the original teachers? The tablet itself offers no answers, just numbers pressed into clay with the confidence of established knowledge. But in its silence, it corroborates what the Sumerian myths insisted. This knowledge came from before. It was inherited, not invented. It was the me, passed down from a source that the clay remembers, but history has forgotten. Stand in the archive with that tablet, its cuneiform still sharp after 40 centuries. Feel the weight of what it represents, not just mathematical sophistication, but the burden of inheritance, the responsibility of preservation. The Sumerians received this knowledge and worked to transmit it faithfully, copying it onto tablets that would outlast empires, that would survive floods and fires, and the collapse of their civilization itself. They succeeded. The mathematics survived. But the source, the original from which these copies were made, remains hidden. It exists only as implication, as the logical necessity that precedes the evidence we possess. Someone taught the teachers. Someone calculated these triples before they were pressed into Sumerian clay. Someone, somewhere, somewhen, possessed the me before they were transmitted to Sumer. And that someone is missing from our history, present only as absence, as the gap in the narrative that grows more glaring the more closely we examine what the Sumerians actually achieved. There's a particular moment in archaeological excavation when the soil changes character. You're working through layers of occupation debris, pottery shards and ash, and the compressed remains of daily life, and then suddenly the texture shifts. The color changes. The density alters beneath the trowel. You've hit a boundary, a discontinuity in the earth that marks not just time, but event. In 1929, Leonard Woolley experienced this moment while excavating the ancient city of in southern Iraq. He was searching for evidence of early Sumerian civilization, working his way down through successive occupation layers, when his workers struck something unexpected. Clean clay. Sterile, water-deposited clay with no artifacts. No occupation debris. No signs of human presence. Just sediment, meters thick, separating the ruins above from whatever lay beneath. Woolley was a meticulous archaeologist, trained in the rigorous methods of early 20th century fieldwork. He understood stratigraphy, the principle that layers of earth accumulate in sequence, with the oldest at the bottom and the most recent at the top. When he encountered the clay layer, he recognized it immediately for what it was: flood deposit. Not the residue of seasonal inundation, the regular overflow that enriched Mesopotamian farmland and made civilization possible in this arid region. This was catastrophic deposition, the kind that only occurs when water overwhelms the landscape completely, drowning settlements and leaving behind meters of sterile sediment when it finally recedes. The layer was 3 meters thick in some places. 3 meters of clay laid down all at once, burying everything beneath it and resetting the archaeological clock to zero. But what struck Woolley most forcefully wasn't the flood layer itself. It was what lay on either side of it. Above the clay, Sumerian civilization appeared already sophisticated, already possessing writing and mathematics, and monumental architecture. The pottery was refined, the building techniques advanced, the administrative systems complex. Below the clay, in the settlements that predated the flood, there were traces of something else. The flood layer appears not just at but at multiple sites across Mesopotamia. Excavations at Uruk, at Kish, at Shurupak all revealed similar discontinuities, sterile clay deposits separating earlier occupation from later rebuilding. The dates vary slightly from site to site, as one would expect from a large-scale inundation that progressed across the landscape over time. But the pattern is consistent. Around 3000 BCE, perhaps slightly earlier, water overwhelmed the Mesopotamian plain. The flood wasn't localized, wasn't a single river breaking its banks. It was systemic, covering vast areas of the Tigris-Euphrates Valley and leaving behind sediment that would preserve the evidence of catastrophe for archaeologists to find 5,000 years later. The Sumerian texts describe this event with clinical precision. The flood appears in multiple documents, most famously in the instructions to Ziusudra, the Sumerian Noah, who receives warning of impending catastrophe and builds a vessel to preserve life. But the flood appears also in more mundane texts. King lists, temple records, administrative documents that mark a clear division between what came before the water and what came after. The Sumerian king list, one of the most important historical documents to survive from ancient Mesopotamia, presents a chronology of rulers going back to the beginning of kingship. And then, after listing kings who reigned for impossibly long periods, the text makes a simple, devastating statement. Then, the flood swept over. After the flood, kingship descended from heaven once more. The document treats the inundation as absolute historical fact, a catastrophic interruption in the continuity of civilization. The conventional interpretation of these texts and archaeological evidence has always been measured, cautious. The flood happened, certainly. Regional catastrophic inundations are well documented in Mesopotamian history. But the biblical connections, the mythological overlay, the presence of flood narratives in multiple ancient cultures all contributed to skepticism about treating the Sumerian accounts as literal history. Scholars preferred to see the flood stories as cultural memory, mythologized and exaggerated, describing perhaps a particularly severe seasonal inundation that became legendary over generations of retelling. The sterile clay layers were acknowledged but not emphasized, treated as interesting geological data points rather than evidence of civilization-ending catastrophe. But here's what the cautious interpretations must explain away. The clay isn't seasonal deposition. Geological analysis confirms this. The sediment shows characteristics of rapid deposition from sustained, massive inundation. The particle size distribution, the absence of organic material, the uniformity of the deposit, all indicate catastrophic flooding on a scale that would have been unsurvivable for anyone caught in its path. This wasn't a bad flood season. This was the kind of event that destroys civilizations, that forces survivors to flee to higher ground and wait for the waters to recede, that resets the landscape completely. And when it was over, when people returned to the floodplain to rebuild, they brought knowledge with them. Mathematical knowledge, astronomical knowledge, architectural techniques, administrative systems. The flood didn't erase civilization. It interrupted it. Consider tablet CBS 10673 in this context. The mathematics it contains predates the flood layers at some sites, postdates them at others, depending on which chronology you follow and how you date the various strata. But what's clear is that the knowledge encoded on the tablet survived the catastrophe. Either it was copied before the flood and preserved through the crisis, or it was part of the knowledge brought back after the waters receded. Either way, the tablet represents continuity across catastrophe. The Pythagorean triples, the astronomical calculations, the systematic mathematical notation all bridge the gap that the flood created. This suggests intention, deliberate preservation, a conscious effort to ensure that critical knowledge wouldn't be lost, even in the face of civilization-ending disaster. The Sumerian texts make this explicit. Multiple documents describe the preservation of knowledge before the flood. The god Enki, who warns Ziusudra of the coming disaster, instructs him not just to save lives, but to preserve understanding. Some versions of the story describe tablets buried before the flood, to be retrieved after the waters recede. Others mention knowledge transmitted orally, memorized and repeated until it could be written again. The texts treat knowledge preservation as equally important as physical survival, as if the Sumerians understood that civilization requires more than just survivors. It requires memory, technique, the accumulated understanding that makes sophisticated culture possible. And they worked consciously to ensure that memory would survive. The silence in the flood layers is profound. For a period that might have been months or years, the Mesopotamian plain was empty of human presence, covered by water that erased settlements and drowned the landscape. During that silence, knowledge existed only in the minds of survivors, in whatever they could carry to safety, in oral traditions and portable records. And then, when the water finally receded and people returned to rebuild, that knowledge came back with them. The mathematics reappeared. The astronomy continued. The administrative systems resumed function. The civilization that emerged above the flood layer looked remarkably similar to the civilization that had existed below it, suggesting that the cultural continuity survived even when the physical continuity was broken. Woolley excavated down through that flood layer, his workers removing buckets of sterile clay that represented catastrophe and survival in equal measure. He found the boundary between before and after, the geological evidence of disruption that the Sumerian texts had described all along. And above the clay and below it, he found evidence of sophisticated culture, of organized society, of people who possessed knowledge that allowed them to build cities and track the stars and record their understanding in permanent form. Mathematics doesn't lie. It can be misunderstood, misapplied, or incompletely grasped, but the relationships it describes remain constant, regardless of who observes them or when. A right triangle drawn in Sumerian clay obeys the same geometric principles as one constructed on a computer screen today. The ratio between a circle's circumference and its diameter was the same in 1800 BCE as it is now. When we examine ancient mathematics, we're not evaluating subjective cultural interpretations. We're assessing objective competence in understanding relationships that transcend time and culture. And when we examine tablet CBS 10673 with this understanding, when we analyze not just what it contains, but what that content implies about the minds that created it, we confront a sophistication that shouldn't exist for another 3,000 years. The tablet contains more than Pythagorean triples. That recognition, groundbreaking as it was when Neugebauer first published his analysis, represents only the surface layer of what the clay preserves. Deeper examination reveals that the triples aren't randomly selected or arbitrarily arranged. They're organized according to a specific mathematical principle. They're ordered by the ratio of the shorter leg to the hypotenuse, which corresponds to the trigonometric function we now call sine. The Sumerians were calculating trigonometric ratios. They were working with concepts that wouldn't be formally defined until Hipparchus in the 2nd century BCE, and wouldn't be fully developed until Indian mathematicians refined them over a millennium later. The tablet demonstrates not just knowledge of geometric relationships, but understanding of the analytical tools necessary to manipulate and systematize that knowledge. Consider what this requires. To organize Pythagorean triples by trigonometric ratio, you must first recognize that such ratios exist. You must understand that the relationship between a right triangle's sides can be expressed as proportions, and that these proportions remain constant for all triangles with the same angles regardless of their size. This is not intuitive knowledge. It's abstract mathematical thinking of the highest order, the kind that requires conceptual frameworks sophisticated enough to separate the idea of proportion from the physical measurements that embody it. The Sumerians who created this tablet weren't just calculating numbers. They were thinking in terms of mathematical relationships, manipulating abstract concepts with confidence that suggests deep theoretical understanding. But the sophistication goes deeper still. Modern analysis of the tablet's numerical sequences reveals something even more unsettling. The calculations show evidence of algorithmic generation. The Pythagorean triples weren't discovered through trial and error, testing number after number to see which combinations satisfied the equation. They were generated using a systematic method, a formula that could produce an infinite series of valid triples. Mathematicians have reconstructed the likely algorithm. Take any two numbers where one is larger than the other, square both numbers, and use those squares along with their difference to generate a Pythagorean triple. This method works perfectly, producing valid triples with mechanical reliability. The Sumerians possessed this algorithm 1800 years before the birth of Christ. The implications are staggering. Algorithm development represents a conceptual leap beyond simple calculation. It requires recognizing patterns in numerical relationships, abstracting those patterns into general principles, and then applying those principles systematically to generate new results. This is advanced mathematical thinking, the foundation of modern computational mathematics. We don't expect to find it in the ancient world because we assume it requires technological infrastructure, institutional support, generations of accumulated knowledge building toward breakthrough insights. Yet here it is, pressed into clay with casual competence, as if algorithmic thinking were as ordinary as addition and subtraction. The mathematical content of the tablet also reveals understanding of second-degree algebraic equations. Several of the number sets can only be generated by solving quadratic equations, expressions that involve variables raised to the second power. Solving such equations requires techniques that weren't formally developed in the Western mathematical tradition until the Islamic Golden Age, when mathematicians like al-Khwarizmi created the field we now call algebra. That was in the 9th century CE, 2,700 years after the tablet was created. Yet the Sumerian scribes were solving quadratic equations with precision, generating correct solutions, demonstrating mastery of algebraic techniques that history credits to cultures separated from them by millennia. Conventional explanations struggle against this evidence. Some scholars suggest that the Sumerians might have stumbled upon these techniques through purely practical means, that centuries of land surveying and construction might have gradually revealed these mathematical relationships through empirical observation. But empirical observation produces approximations, not exact solutions. It yields rules of thumb, not systematic algorithms. The mathematics on tablet CBS 10673 is too precise, too systematic, too theoretically sophisticated to be the product of accumulated practical experience. It reads like academic mathematics, like the work of people who understood not just how to calculate, but why the calculations worked. Others propose that perhaps we're overinterpreting the tablet, projecting modern mathematical concepts onto ancient calculations that meant something different to their creators. But mathematics is universal. A Pythagorean triple is a Pythagorean triple, regardless of what culture calculates it or what they call it. The relationship between the numbers doesn't change based on interpretation. When Sumerian scribes arranged 15 Pythagorean triples in order of their trigonometric ratios, they were performing an operation that has only one mathematical meaning. There's no alternative interpretation that makes this less sophisticated or more primitive. The mathematics speaks for itself, and what it says is clear. The people who created this tablet understood advanced mathematical concepts. The absence of pedagogical texts makes the sophistication even more inexplicable. When we examine mathematics education in other ancient cultures, we find teaching materials, problems with solutions, exercises of increasing difficulty, explanations of methods and techniques. These pedagogical texts show the learning process, the transmission of knowledge from teacher to student. But for Sumerian mathematics, such texts are largely absent. We have tables like CBS 10673, which present finished calculations. We have multiplication tables and reciprocal tables, tools for computation. But we don't have the explanatory texts that should accompany such advanced mathematics. It's as if we've found a calculus textbook, but no algebra primer, advanced applications, but no introduction to fundamentals. This pattern suggests once again that Sumerian mathematics wasn't being developed, but preserved. The tablets we possess aren't the work of mathematicians discovering new principles. They're the work of scribes copying existing knowledge, maintaining traditions they'd inherited from sources that remain frustratingly invisible. The mathematics appears complete because it was complete when the Sumerians received it. They were preserving what they'd been given, transmitting it forward through the technology of writing, ensuring it wouldn't be lost, even if the original understanding faded. The tablets are archives, not laboratories. They document knowledge that already existed in mature form. Stand in the archive again, your eyes on that tablet with its 15 rows of numbers. Each triple is correct. Each calculation is precise. Each organizational principle reflects deep mathematical understanding. There are no mistakes here, no false starts, no evidence of learning. The mathematics appears with the confidence of mastery, pressed into clay by hands that knew exactly what they were doing, even if they might not have fully understood why it worked. And in that perfection, in that complete absence of error or evolution, the tablet poses its most unsettling question. If this is copied knowledge, preserved rather than discovered, where is the original? Where are the mathematicians who first developed these algorithms, who first recognized these patterns, who first understood these principles deeply enough to systematize them into teachable form? The clay offers no answers, just numbers that refuse to fit the comfortable narrative of gradual human progress. The mathematics that shouldn't exist does exist, preserved in a tablet that has waited 40 centuries for us to finally understand what we're looking at. And now that we do understand, now that we've recognized the sophistication encoded in those cuneiform marks, we're left with the weight of implication. Mathematics this advanced requires theoretical foundations we can't find, teaching traditions we can't trace, institutional support we can't document. It requires, ultimately, a source that remains hidden, present only as logical necessity, as the gap in our history where the origin of this knowledge should be, but isn't. Every genuine discovery leaves traces of its discovery. When humans learn something new, when they push into unknown territory and map relationships they've never understood before, the process is messy. There are false starts, incorrect hypotheses, calculations that almost work but fail at the crucial moment. There are corrections, erasures, marginal notes where someone realized their error and tried again. The history of human learning is a history of mistakes gradually refined into understanding, of wrong answers that teach us where the right answers must be. This is true across all domains of knowledge, from mathematics to medicine, from astronomy to engineering. Learning has a signature, a characteristic pattern of error and correction that marks the difference between discovery and mastery. And that signature is completely absent from Sumerian mathematics. Examine tablet CBS 10673 with this understanding. Look at the calculations, the systematic arrangement of Pythagorean triples, the algorithmic precision of the numerical generation. There are no corrections. The stylus marks are clean, confident, pressed into the clay with the certainty of someone who knows exactly what they're writing. There are no erasures, no scratched-out errors, no marginal notations indicating that the scribe caught a mistake and corrected it. The mathematics appears perfect on the first attempt, as if the person holding the stylus was copying from a source rather than working through problems. This is the handwriting of transmission, not discovery. This is what preservation looks like when rendered in clay. The absence of error isn't limited to this single tablet. Across the corpus of Sumerian mathematical texts, the pattern repeats with uncomfortable consistency. Multiplication tables present correct products with no miscalculations. Reciprocal tables list inverse relationships with perfect accuracy. Problem texts pose complex scenarios and provide correct solutions without showing the work, without demonstrating the logical steps that lead from question to answer. The mathematics appears already solved, already understood, already mastered. Where are the practice problems that got the answers wrong? Where are the student exercises that show fumbling toward competence? Where is the learning curve that must precede expertise? This pattern extends beyond mathematics into every domain where we can assess Sumerian competence. Their earliest architectural texts describe construction techniques that work, that produce stable structures, that demonstrate understanding of load-bearing principles and material properties. There are no records of collapsed buildings, no accounts of trial and error in developing construction methods. The techniques appear functional from the beginning, as if someone already knew which methods would succeed and which would fail. Their irrigation engineering shows the same troubling perfection: canals designed with gradients that prevent silting, water distribution systems that serve multiple fields efficiently, techniques that demonstrate sophisticated understanding of hydrology and civil engineering. But where are the failed experiments? Where are the irrigation systems that didn't work, that taught the Sumerians what not to do? The conventional response invokes lost evidence. Perhaps the mistakes existed but weren't recorded, scholars suggest. Perhaps failed attempts were destroyed or discarded, leaving only the successful examples for us to find. Perhaps the learning process happened in media that didn't survive, in oral traditions or temporary materials that the archaeological record can't capture. These explanations are possible, technically plausible, but they require us to believe that Sumerian record-keeping was strangely selective. They preserved grain receipts, temple inventories, administrative correspondence so mundane it borders on tedious. They recorded lawsuits, property disputes, loans, and their repayment. They documented everything with obsessive thoroughness. Yet somehow, all the mathematical errors, all the failed architectural experiments, all the engineering mistakes vanished completely from the record. The selectivity required for this explanation is itself suspicious. Consider also the speed of Sumerian development. Civilization as we recognize it appears in Mesopotamia around 3200 BCE. Within 2 centuries, perhaps less, the Sumerians possessed sophisticated writing, complex mathematics, monumental architecture, advanced metallurgy, and organized bureaucratic states. 200 years is approximately 8 human generations. In 8 generations, they went from no writing system to producing texts that demonstrate advanced mathematical competence. In 8 generations, they developed astronomical observations sophisticated enough to calculate planetary synodic periods. In 8 generations, they built cities with populations in the tens of thousands, complete with sanitation systems, defensive walls, and temples that dominated the skyline. This isn't impossible, but it's extraordinarily rapid, faster than cultural development in any other context we can observe historically. For comparison, consider Egypt, another early civilization that developed sophisticated mathematics and monumental architecture. Egyptian civilization shows clear developmental stages. We can trace the evolution of their writing system from simple pictographs to complex hieroglyphic script over centuries. We can observe the progression of their pyramid-building techniques, from experimental step pyramids that partially collapsed to the geometric perfection of the Giza pyramids, refined through generations of accumulated experience. We can see their mathematics developing, with earlier texts showing simpler operations and later texts demonstrating more sophisticated techniques. Egypt's trajectory looks like learning, like human beings figuring things out through trial and error, extended across centuries. Sumer's trajectory looks like sudden competence, like knowledge that appeared rather than evolved. The problem becomes acute when we examine Sumerian astronomical texts. The precision demonstrated in tracking Venus, the accuracy of their synodic period calculations, the sophisticated understanding of celestial mechanics, all require sustained observation over decades or longer. You cannot calculate Venus's 584-day synodic period without observing multiple complete cycles. You cannot distinguish apparent motion from actual motion without comparing observations across years. This kind of observational astronomy requires institutional continuity, dedicated observers, systematic record-keeping extended across generations. Yet the earliest Sumerian astronomical texts, the ones closest to the civilization's emergence, already demonstrate this precision. Where are the decades of observation that must precede such knowledge? Where are the preliminary calculations, the approximations that get refined into accuracy? They're absent, as if the Sumerians started observing the sky with perfect understanding already in place. This pattern of perfect knowledge suggests something deeply uncomfortable. The Sumerians weren't discovering their mathematics, astronomy, and engineering. They were applying them. They possessed templates, exemplars, perhaps even inherited texts or oral traditions that provided the frameworks they needed. Their task wasn't to develop these fields from first principles, but to implement knowledge that already existed in some form. This explains why there are no mistakes in the record. You don't make errors when you're copying. You don't fumble through trial and error when you're following instructions. The absence of learning curve isn't because the Sumerians were impossibly brilliant. It's because they weren't learning. They were remembering, preserving, transmitting what had been given to them. Tablet CBS 10673 embodies this uncomfortable reality. Its mathematical perfection isn't the perfection of genius discovering new truths. It's the perfection of faithful copying, of preservation rather than innovation. The scribe who pressed those numbers into clay wasn't solving Pythagorean triples for the first time. They were recording solutions that already existed, maintaining knowledge that had been passed down through teaching traditions whose origins remain invisible to us. The tablet is an archive, not a laboratory notebook. It documents understanding rather than discovery. And in that documentation, in that clinical presentation of advanced mathematics, with no accompanying explanation of how it was derived, the tablet reveals its true, its inheritance made physical, knowledge from before pressed into clay so it could survive into after. The weight of this realization is profound. It means we're not looking at the beginning of human mathematical sophistication. We're looking at a middle chapter, at people working from sources we can't see, preserving knowledge they received rather than originated. The tablet's perfection isn't impressive achievement. It's evidence of absence, pointing toward a gap in the historical record where the true origin of this mathematics should be, but isn't. The Sumerians mastered mathematics without the mistakes that mastery requires. They possessed knowledge without the learning curve that knowledge demands. And that impossibility, that violation of every pattern we observe in human development, suggests that the comfortable narrative of civilization's birth is incomplete. Something came before. Someone taught the teachers. And that source, that origin point for the knowledge the Sumerians preserved so faithfully, remains hidden, present only as logical necessity, as the explanation that the evidence requires, but history has failed to preserve. When confronted with evidence that challenges comfortable narratives, human institutions respond with explanations designed to preserve the status quo. This is not conspiracy or deliberate suppression. It's the natural conservatism of knowledge systems that have invested heavily in particular interpretations of the past. When tablet CBS 10673 revealed its mathematical sophistication, when the Pythagorean triples and trigonometric ratios and algorithmic generation became undeniable, the academic community didn't abandon the narrative of gradual human progress. Instead, they proposed alternative explanations, hypotheses meant to reconcile the troubling evidence with the accepted timeline of civilization's development. Each explanation seemed reasonable on its surface, but each one, when examined closely, dissolved into implausibility when confronted with the full weight of what the tablet actually contains. The first hypothesis proposed misdating. Perhaps the tablet wasn't from 1800 BCE after all. Perhaps the archaeological context was confused, the stratigraphic layers misread, the artifact itself displaced from its original position and incorporated into older sediment layers. This would be convenient. If the tablet could be moved forward in time, closer to the Greek mathematical revolution, its sophistication would become less anomalous, more aligned with what we expect from ancient mathematics. But the stratigraphy at Nippur, where the tablet was excavated, is among the best documented in Mesopotamian archaeology. The occupation layers are clear, the dating confirmed through multiple independent methods including ceramic typology, architectural styles, and textual cross-references. The tablet comes from the Old Babylonian period, approximately 1800 BCE. This dating isn't approximate or uncertain. It's definitive, corroborated by everything surrounding the artifact in its archaeological context. Moreover, the tablet isn't unique. Similar mathematical texts exist from the same period, demonstrating comparable sophistication. The famous Plimpton 322 tablet, housed at Columbia University, contains a different set of Pythagorean triples, arranged according to sophisticated mathematical principles. It dates to the same period, excavated from the same general region, part of the same mathematical tradition. Other tablets demonstrate advanced algebraic techniques, geometric understanding, and numerical sophistication, all dating to the Old Babylonian period. To dismiss CBS 10673 as misdated, you must dismiss an entire corpus of mathematical texts, all of which corroborate each other's sophistication, and all of which come from securely dated contexts. The misdating hypothesis doesn't explain the evidence. It simply refuses to accept it. The second hypothesis suggests symbolic rather than literal interpretation. Perhaps the mathematical relationships on the tablet weren't meant as actual calculations, but as religious or ceremonial symbols. Perhaps the numbers held mystical significance rather than practical, mathematical meaning. This explanation appeals to modern assumptions about ancient thinking, the idea that primitive cultures confused mathematics with magic, that they invested numbers with supernatural properties rather than understanding them as abstract relationships. But this hypothesis crumbles when confronted with the clinical of the tablet's contents. There are no religious invocations, no prayers or ritual instructions. The text is purely mathematical, presented in the same bureaucratic style used for grain inventories and administrative records. The calculations are correct, the methods systematic, the organization logical. This isn't mysticism. This is mathematics, performed with competence that indicates complete understanding of what the numbers represent. Furthermore, we possess other Sumerian texts that demonstrate clear distinction between symbolic and practical mathematics. Temple texts that assign numerological significance to deities use different formatting, different language, different organizational principles than mathematical teaching tablets. The Sumerians knew the difference between numbers as symbols and numbers as tools. They maintained separate traditions for each. CBS 10673 belongs firmly to the practical mathematical tradition, not the symbolic one. The hypothesis that these are religious symbols rather than actual calculations requires ignoring how the Sumerians themselves categorized and presented mathematical knowledge. It imposes modern misconceptions about ancient thinking onto evidence that explicitly contradicts those misconceptions. The third hypothesis proposes reinterpretation through modern mathematical lens. Perhaps we're projecting contemporary concepts onto ancient calculations, seeing sophistication that the original creators never intended. Perhaps the Pythagorean triples were discovered through purely geometric means, through practical construction techniques that happened to generate these numerical relationships without requiring abstract mathematical understanding. Perhaps the organization of the triples is coincidental, not evidence of trigonometric knowledge. This explanation attempts to minimize the implications by suggesting that the Sumerians stumbled upon correct mathematics without understanding what they'd found. But this hypothesis requires believing in extraordinarily unlikely coincidences. The triples are organized precisely according to trigonometric ratios. The arrangement isn't random or arbitrary. It follows a specific mathematical principle that has only one interpretation, regardless of what culture examines it. Multiple independent translations of the tablet, performed by scholars from different academic traditions and theoretical orientations, all arrive at the same conclusions. The mathematics is sophisticated, systematic, and demonstrative of advanced theoretical understanding. When German mathematicians analyze the tablet, they see trigonometric organization. When American scholars examine it, they find algorithmic generation. When British historians study it, they recognize abstract mathematical thinking. The interpretations converge because the mathematics itself is unambiguous. There's no alternative reading that makes the tablet less sophisticated or more primitive. The numbers say what they say. The relationships exist regardless of interpretation. Suggesting that modern scholars are overreading the evidence requires explaining why independent analyses from completely different perspectives all reach identical conclusions about the tablet's mathematical content. The fourth hypothesis invokes practical origin through trial and error. Perhaps generations of Sumerian builders and surveyors working on construction projects over centuries gradually accumulated empirical knowledge about right triangles and eventually codified that knowledge into mathematical tables. This seems plausible until you examine the specific triples on the tablet. Some of these number sets have no practical application in construction. The triple 12,709, 13,500, 18,541 isn't something you'd encounter while building a temple or measuring a field. It's a purely theoretical calculation, interesting mathematically, but useless practically. The presence of such triples indicates that the tablet's purpose wasn't practical record-keeping, but mathematical exploration, the kind of abstract thinking that requires theoretical frameworks rather than accumulated experience. Each hypothesis, examined individually, seems to offer a path back to comfortable explanations. Perhaps the dating is wrong, or the interpretation flawed, or the sophistication exaggerated, or the origin more mundane than it appears. But these explanations don't exist in isolation. They must account for the complete picture, the precise dating, the unambiguous mathematics, the absence of developmental stages, the systematic organization, the algorithmic generation, the trigonometric principles, the correlation with astronomical knowledge, the flood layers, the sudden emergence of sophistication, the mythological claims of inherited knowledge. Each piece of evidence eliminates possible explanations. Taken together, the evidence points toward a conclusion that conventional archaeology and history resist accepting. The resistance is understandable. The conclusion the evidence suggests rewrites fundamental assumptions about human civilization's development. It implies that the Sumerians weren't the first, that sophisticated culture existed before the beginning we've identified, that catastrophe interrupted continuity and forced survivors to rebuild from inherited knowledge rather than discovered principles. This interpretation challenges the progressive narrative of human achievement, the comforting story that we've climbed steadily upward from primitive beginnings to modern sophistication. The evidence suggests instead that civilization is cyclical, that knowledge can be lost as easily as gained, that we might be looking not at the dawn of human capability, but at its twilight, at people preserving fragments of understanding they received from sources that catastrophe erased from the physical record. Tablet CBS 10673 sits at the center of this uncomfortable realization. Its mathematics cannot be explained away by dating errors, symbolic interpretation, modern projection, or practical origin. The calculations are too precise, too sophisticated, too systematically organized to fit any of the comfortable explanations. The tablet demands that we accept what it demonstrates. The Sumerians possessed mathematical knowledge that they shouldn't have been able to develop in the time frame available. They inherited it rather than invented it. And that inheritance points backward, toward a source that conventional history has no room for, toward teachers whose existence the evidence requires, but the archaeological record fails to confirm. The hypotheses proposed to explain the tablet away don't survive scrutiny. What remains is the harder truth, the one the clay has been whispering for 40 centuries. This knowledge came from before, from somewhere else, from people we've forgotten how to see. The Sumerian king list is one of the most extraordinary documents to survive from the ancient world, not for what it records, but for how it records it. The text exists in multiple copies, inscribed on clay tablets and prisms over several centuries, each version preserving with meticulous care a chronology of rulers stretching back to the very beginning of kingship itself. The list begins with a simple declaration that, after kingship descended from heaven, the first city to receive it was Eridu. Then it names the rulers, one by one, along with the length of their reigns. And here the document becomes deeply unsettling. The antediluvian kings, those who ruled before the flood swept over the land, reigned for periods that defy human lifespans. 28,800 years, 36,000 years, 43,200 years. These aren't symbolic numbers or religious metaphors. They're presented in the same clinical format used for historical kings, whose reigns we can verify through other sources. The conventional interpretation treats these enormous numbers as mythological, as the inevitable exaggeration that primitive cultures applied to their legendary past. Ancient peoples didn't understand deep time, the argument goes, so they expressed the concept of great antiquity through impossibly long reigns. But this explanation requires ignoring how the Sumerians used numbers elsewhere. Their mathematical texts demonstrate precise understanding of numerical relationships. Their astronomical calculations show sophisticated grasp of temporal cycles. Their administrative records track grain storage and labor allocation with a counting precision that modern bureaucracies would recognize. The Sumerians weren't confused about numbers or time. When they recorded that Alulim reigned for 28,800 years in Eridu, they were preserving a number that meant something specific, even if that meaning has become opaque to us. Modern analysis of these antediluvian reign lengths reveals a pattern that conventional interpretations dismiss too quickly. The numbers aren't random. They're multiples of 3,600, the Sumerian numerical unit called a sar. Alulim's reign of 28,800 years equals 8 sar. Alaljar's reign of 36,000 years equals 10 sar. The precision is systematic, suggesting these aren't mythological inventions but calculations, numbers derived through some method that made sense to their creators. And 3,600 isn't arbitrary in Sumerian thought. It's deeply connected to their astronomical observations, specifically to the precessional cycle of the Earth's axis, which completes a full rotation approximately every 25,920 years. The numbers in the king list might not be recording years of human rule. They might be recording astronomical cycles, cosmic time measured in units that dwarf human experience. This interpretation gains support from what the king list says about itself. After listing 8 rulers whose combined reigns span 241,200 years, the text makes a simple, devastating statement. These were the kings before the flood. Then the flood swept over. After the flood, kingship descended from heaven once more. The document treats the deluge as absolute historical fact, a catastrophic interruption that ended one age and began another. The kings who ruled after the flood had normal human lifespans, reigning for decades rather than millennia. The chronology becomes plausible, verifiable through archaeological evidence and cross-referencing with other historical sources. But the antediluvian section remains, preserved with the same care as the historical material, suggesting that the Sumerians considered both sections equally factual, equally worthy of transmission to future generations. If the antediluvian numbers record astronomical cycles rather than human lifespans, what does this tell us about the people who created the king list? It suggests they possessed sophisticated understanding of celestial mechanics, that they tracked precessional movement with precision that requires observational continuity spanning centuries or millennia. It suggests they thought in terms of deep time, measuring history against cosmic cycles rather than human generations. Most significantly, it suggests they were preserving knowledge from before the flood, recording information about a world that the catastrophe had destroyed. The king list isn't just a political document listing rulers. It's an archive, an attempt to preserve chronological information that connects the post-flood world to something that came before, something the flood nearly erased completely. Now reconsider tablet CBS 10673 in this context. The mathematical sophistication it demonstrates, the astronomical knowledge it encodes, the algorithmic thinking it reveals, all suggest inheritance from a culture that possessed advanced theoretical understanding. The king list provides a framework for that inheritance. It describes rulers who governed before the catastrophe, who presided over a civilization sophisticated enough to track astronomical cycles across millennia, to develop mathematics that wouldn't be matched for thousands of years, to build knowledge systems that survived the flood through deliberate preservation. The tablet and the king list corroborate each other. They're both archives of the drowned world, preserving different aspects of what was lost when the water came. The mythological texts expand this picture further. Sumerian literature repeatedly describes the antediluvian world as possessing wisdom that the post-flood world struggled to preserve. The god Enki, guardian of knowledge, takes specific action before the flood to ensure that critical understanding will survive. Some texts describe him instructing chosen individuals to bury tablets before the deluge, preserving written knowledge that could be retrieved after the waters receded. Other texts mention oral transmission, memorization of crucial information so it could be reconstructed when writing became possible again. The mythology frames knowledge preservation as equally important as physical survival, as if the Sumerians understood that civilization requires more than just survivors. It requires continuity of understanding, transmission of techniques, preservation of the accumulated wisdom that makes sophisticated culture possible. This isn't how mythology typically functions. Most creation myths explain origins, not preservation. They describe how the world began, how humans were created, how the gods established order from chaos. But Sumerian mythology consistently emphasizes restoration, transmission, the passing of knowledge from before the catastrophe to after it. The me, those fundamental aspects of civilization, aren't described as new inventions, but as recovered treasures, knowledge that existed before and had to be retrieved, redistributed, re-established in the post-flood world. The emphasis on recovery rather than creation suggests that Sumerian mythology preserves actual cultural memory, that it's describing real historical processes through the only narrative framework available to Bronze Age peoples. The flood layers excavated at and other Mesopotamian sites provide physical corroboration for the catastrophe the texts describe. The sterile clay deposits, 3 meters thick in places, represent genuine disaster, inundation on a scale that would have destroyed settlements and forced survivors to flee. When the waters finally receded and people returned to rebuild, they brought knowledge with them. Mathematical knowledge encoded on tablets like CBS 10673. Astronomical understanding preserved in observational records. Architectural techniques, metallurgical processes, administrative systems, all the sophisticated elements of civilization that reappeared in the post-flood world, already functional, already complete. The physical evidence and the textual record align. Catastrophe happened. Civilization survived. Knowledge was preserved through the disaster and transmitted to the rebuilt world. But if knowledge survived, if the me were successfully transmitted across the catastrophe, what about the people who originated that knowledge? The antediluvian kings who reigned for astronomical cycles, who governed cities before the flood, who presided over the civilization that developed the mathematics and astronomy the Sumerians inherited. Where did they come from? The king list offers no origin for them. They simply exist, present at the beginning of the chronology with no explanation of how they acquired their knowledge or who taught them. This is the gap at the heart of the archive, the missing chapter that should explain the source but doesn't. The Sumerians preserved what they could, transmitted what they inherited, but the ultimate origin of that inheritance remained beyond their reach, lost in a past that even the king list's extraordinary chronology couldn't illuminate. Tablet CBS 10673 and the Sumerian king list together form a testament to deliberate preservation across catastrophe. They represent different aspects of the same project, maintaining civilizational knowledge when the physical continuity of civilization itself has been broken. The tablet preserves mathematics. The king list preserves chronology. Both documents treat their contents with bureaucratic precision, as if accuracy in transmission was paramount, as if the survival of this information mattered more than the survival of the individuals doing the transmitting. And both documents point backward, toward a source that possessed the knowledge first, that originated the mathematics and tracked the astronomical cycles and built the civilization that the flood destroyed. That source remains invisible in the archaeological record, present only as implication, as the necessary precursor to what the Sumerians preserved. But its existence is undeniable. Someone taught the teachers. Someone calculated before the calculations were copied into Sumerian clay. Someone watched the stars before the Sumerians recorded what they saw. The archive preserves the inheritance, but the origin of that inheritance lies beneath the floodwaters, in the drowned world that history has forgotten, but the evidence insists once existed. In a climate-controlled archive at the University of Pennsylvania Museum, tablet CBS 10673 rests in its case, protected from the air that would slowly return it to dust. The cuneiform marks are still sharp, still legible after 40 centuries of waiting. The mathematical relationships encoded in those wedge-shaped impressions remain true, unchanged by time or interpretation. The Pythagorean triples still satisfy their equations with perfect precision. The trigonometric ratios still organize themselves according to principles that transcend culture and era. The clay remembers what it was taught to remember, preserving knowledge that its creators worked desperately to transmit across the gap that catastrophe creates between one world and the next. Stand before that case and feel the weight of what you're looking at. This isn't just an ancient mathematical document. It's a message across time, sent by people who understood that knowledge is more fragile than the clay that preserves it. The tablet represents a choice made in the face of catastrophe, to preserve rather than surrender, to transmit rather than forget, to ensure that what was learned wouldn't have to be learned again from nothing. The Sumerians who created this tablet and the thousands like it, scattered across museum archives worldwide, were building an archive against forgetting, pressing understanding into permanent form, because they knew, from experience recorded in their flood layers and their king lists and their mythology, that civilization can end. That knowledge can be lost, that the work of millennia can vanish in a generation if no one makes the conscious effort to preserve it. The sophistication encoded in the tablet's calculations tells us that this wasn't the first time knowledge had been preserved. The mathematics is too complete, too systematic, too free from error to represent original discovery. It reads like curriculum, like teaching material designed to transmit understanding from one generation to the next. But if it's curriculum, who designed the original course? If it's teaching material, who were the first teachers? The tablet points backward toward a source it cannot name, toward origins that remain hidden beneath floodwaters and accumulated sediment, and the simple passage of time that erases physical evidence while leaving mathematical truth intact. The Sumerians inherited this knowledge. They preserved it faithfully, copying it onto clay with bureaucratic precision. But they couldn't tell us where it came from originally, because they themselves had inherited it from sources that catastrophe had already made invisible. This pattern of inheritance rather than invention challenges fundamental assumptions about human progress. We want history to be linear, building steadily from primitive beginnings toward modern sophistication. We want each generation to stand on the shoulders of the previous one, advancing incrementally through accumulated knowledge and refined technique. The comfortable narrative says that we've climbed continuously upward from stone tools to spacecraft, from counting on fingers to quantum mechanics, through an unbroken chain of discovery and innovation. But the evidence pressed into Sumerian clay suggests something more troubling, that progress isn't linear but cyclical, that civilization rises and falls in waves separated by catastrophes that force survivors to rebuild from inherited fragments rather than complete understanding. The flood layers excavated at and across Mesopotamia provide physical testimony to this cyclical pattern. Below the sterile clay, evidence of sophisticated culture. Above it, the same sophistication resumed, as if the interruption was temporary rather than permanent. The knowledge survived because people chose to preserve it, because they understood that civilization without memory is just organized survival, waiting for the next disaster to reset everything to zero. The Sumerians transmitted their inheritance forward through writing, through the revolutionary technology of pressing thought into clay that would outlast empires. And we, 40 centuries later, are the beneficiaries of their choice, reading their mathematics and recognizing in it understanding that still holds true, still functions, still describes relationships that govern reality regardless of who observes them or when. But here's the weight that settles in the chest when you truly grasp what the tablet represents. We are now the inheritors. We possess knowledge accumulated over millennia, preserved in forms more permanent than clay, digital archives, genetic libraries, mathematical frameworks, scientific understanding of physics and chemistry and biology and astronomy that would seem like magic to any previous era. We have more knowledge available instantly than the entire ancient world possessed collectively. And yet, how much of it do we actually understand? How many of us could rebuild civilization if catastrophe required it? Could you calculate a Pythagorean triple without your phone? Could you track planetary movements without computer assistance? Could you preserve even a fraction of what you know if the infrastructure that stores and transmits information suddenly vanished? The Sumerians faced this question after their flood and answered it through deliberate preservation, through choosing what was essential enough to commit to permanent record. They preserved mathematics because it was foundational, necessary for everything from architecture to astronomy to administration. They preserved astronomical knowledge because understanding celestial cycles meant understanding time itself, the framework within which all other knowledge operated. They preserved their king lists because chronology grounds culture, connects the present to the past, and suggests continuity into the future. What they preserved tells us what they considered essential for civilization to continue. And in their choices, we see a mirror reflecting our own vulnerabilities. What would we preserve? What do we consider so fundamental that losing it would mean losing civilization itself? The question isn't hypothetical. Climate change threatens agricultural systems that feed billions. Asteroid impacts remain statistically inevitable on geological timescales. Solar storms could disable electrical grids and communications networks. Pandemics demonstrate how quickly global systems can approach collapse. And beyond these physical threats lies the quieter danger of forgetting, of allowing knowledge to exist only in forms dependent on infrastructure that requires constant maintenance. How much of our accumulated understanding would survive if the systems that store and transmit it failed for even a decade? The Sumerians knew this danger intimately. They'd seen knowledge lost, civilization interrupted, understanding reduced to fragments that survivors struggled to preserve. And they responded by creating archives, by pressing knowledge into clay that would outlast the catastrophes they knew from experience would come. Tablet CBS 10673 is one small piece of that archive, one fragment of the vast project of preservation that ancient cultures undertook precisely because they understood civilization's fragility. The tablet has survived floods and fires, conquest and collapse, the fall of empires and the rise of new ones. It has outlasted the civilization that created it, outlasted the language in which it was written, outlasted the cultural context that gave it meaning. And yet the mathematics it contains remains valid, still true, still demonstrating relationships that don't depend on culture or era or interpretation. This is what knowledge looks like when stripped of everything except its essential truth. Numbers that still work, relationships that still hold, understanding that transcends the civilization that first encoded it. The tablet poses a question to us, the latest inheritors of accumulated human knowledge. What will we preserve? When the next catastrophe comes, and history suggests catastrophe is inevitable rather than possible, what understanding is essential enough to commit to forms that will outlast the disaster? The Sumerians chose mathematics and astronomy, chronology and mythology, the frameworks that allow civilization to rebuild rather than start over from nothing. Their choices preserved knowledge across a gap that should have erased it, transmitting understanding from before the flood to after it. We face the same choice, with stakes arguably higher because we have so much more to lose. Our knowledge is vast, but our preservation strategies are untested against the kind of systemic collapse that the archaeological record shows has happened repeatedly throughout human history. In the archive, the tablet waits behind glass, its message still clear after 40 centuries. Knowledge is fragile. Civilization is cyclical. Catastrophe is certain. And in the face of these truths, the only meaningful response is deliberate preservation, conscious transmission. The choice to ensure that what we've learned doesn't have to be learned again from nothing when the next reset comes. The clay remembers this lesson. It has carried it across time, survived the collapse of the civilization that created it, and delivered it to us intact. The question is whether we possess the wisdom to learn from what it teaches, to recognize in its mathematics and its survival both a warning and an instruction. We are not the first civilization to reach sophistication. We will not be the last. But we may be the first with the tools to preserve understanding comprehensively enough that the next inheritors won't have to start over, won't have to rediscover from fragments what we knew completely. The weight of that possibility rests in the clay, patient and enduring, waiting for us to understand what the Sumerians knew. That civilization without memory is just organized forgetting, counting down to the next flood that will sweep over everything we've built and leave only what we've deliberately chosen to preserve. If you enjoyed the video, hit the like button, subscribe, and activate notifications so you don't miss our next videos.